There you go.
All right, awesome. So good to be here. Thanks for the kind invite, and good to see so many familiar faces on the call. Claire and Matt were saying, my name is Dario. I've been at CZI now for 6 years, where I lead our open science program, which includes several initiatives in support of scientific open source. Yeah, so we've been thinking, like Claire we're saying, we've been thinking for several years now about these questions about not just how to evaluate open source software using science for the purpose of running a funding program, but also think about the broader impact and how to really think about beyond the needs of a specific funding program, how to surface the impact that open source is having in science. So today, I think this is gonna be a version of a longer talk that I presented like last year, but I'm hoping to give you a sense of like different tools that we're using and also where we see both gaps and opportunities in like data that is really critical to be able to answer those questions about the impact of software in science. So with that, I'm gonna share my screen.
You should be good. I made you co-host. Good. Got it.
All right. Can you all see this? All right, fantastic. Okay, so a little bit of a teaser of what I'm going to talk about today. I mean, I don't need to explain to this audience why open source is core to science, but it's really core to our mission as a technology-first science funder. And of course, there's a ton of qualitative and quantitative data that exists to assess and understand the growth and maturity of open source software, especially the open source software that's used in science. And as funder institutions, it goes without saying that we need this data to make decisions about what to fund. We cannot fund everything, so we need to make decisions about what to fund. But also, once software is being funded, understand the impact that both our funding is having and then the software project in itself is having in science and more broadly in society. And the main point that I'd like to convey today is that while there's this enormous amount of data that exists to understand software and software communities, there's still some critical type of data that we don't really have at scale that I believe is absolutely fundamental to how we can continue pursuing the support of scientific open source, similar to the program we'll be running. So I'll suggest a few ideas of how we can fix this and some examples of data sets initiatives that were released to that purpose. All right, so starting with a little bit background about our work at CZI and why we fund scientific open source software. So this should be like a self-explanatory slide, but open source is really eating science. And we know that pretty much all the most critical breakthroughs in science of the last 2 decades have been critically enabled by scientific open source software. And this spans like a variety of data-intensive like disciplines, from biomedicine to astronomy, astrophysics to particle physics. There's no single field of science that's not been completely transformed by scientific open source. And when it comes to our specific mission, so at CZI, we have as our 8-year mission, the idea of investing into science technology that will make it possible to cure, prevent, or manage all disease by the end of the century. But concretely, what that means is that we want to superpower in the short term, over the next 10 years, all the tooling and infrastructure that empowers scientists to really help understand the fundamental mechanism behind human biology. And to do that, given that by and large, this is a data-intensive goal, we need to have a thriving ecosystem of software. It looks like my screen is still working. Can you guys still see this?
I see your screen.
All right. And so we're somewhat unusual philanthropy because we have at the same time a technology division. So on top of funding, we also build software ourselves. We have an entire division dedicated to software engineering and products. So we build and maintain our own software products. And we also have a network of research institutes, the do part of our strategy, that basically conduct research and develop their own software solutions. So across all the three different components of our work at CZI, the fund part, which is the one that I'm part of in science programs, the build part, which is really about the science technology team, and the do part, which is about the institutes, open source is really core to everything we're doing, right? And so given the centrality of open source to our mission, back in 2019, we realized that the vast majority of software tools that we wanted to continue to see succeed and that are critical for the functioning of our communities and to the success of our organization, typically, like, these software tools lack dedicated mechanisms for supporting their growth, development, their community engagement, basically all these activities that are absolutely critical for open source communities, as we know, but they are basically impossible to fund through traditional mechanisms of scientific funding. Scientific funding is primarily focused on novelty and on research to produce papers. And so things like supporting community development or a major project addressing tech debt or localization, documentation, all the things that are so critical to open source is really challenging in the context of traditional funding mechanisms. So we thought back then, given the centrality of open source for our mission, what if we start launching a program that will do just that, that will be designed around the needs of maintainers and their communities, and try and see if we can inject some funding in a world that is like dramatically in need of support for some of these activities. And so we launched this program in 2019 called the Essential Open Source Software for Science, short EOSS, with these goals. And the nominal goals is really like a funding and supporting these projects, but really like the overarching and more ambitious goal is to make sure that open source contributions to science become more visible, more fundable, not just by CZI, and also more broadly recognized as a first-class outputs in science. The program grew a lot. So we started in 2019 with a handful of projects, and by the end of the fifth cycle in 2024, we have a pretty large number of projects that we supported through these grants. You'll see many familiar names here if you're in the field that really span a variety of fields. There are both like general purpose software tools using scientific computing, as well as more specialized tools that are used in specific disciplines, particularly in the life sciences, so the area that CZI is primarily supporting. Some quick statistics. So as I said, this started in 2019. We went through 6 funding cycles, invested a total of about $53 million, received over 2,000 applications over time. We're able to fund about 10% of the applications that we received, and 233 individual open source projects. And that's because individual applications can include more than one open source project. The sixth cycle was interestingly our first attempt at building a coalition of funders. So we work with the Wellcome Trust, the Kavli Foundation, and the Research Software Alliance as a non-funding partner to support these efforts. And to our knowledge, even though $53 million is not by any measure like an enormous amount of funding compared to what governments, for example, can invest, this is, to our knowledge, the largest fund to support specifically the needs of core scientific open source communities when it comes to these type of activities that I just mentioned. And so by virtue of running this program, we had to start building out our entire strategy around data that we use to decide what to fund, to study the impact of funded projects, and to really have a better understanding of the program we're running and like what outcomes it's producing. So I'm going to give you here some highlights from the data and the strategy we use to answer those questions. So first off, deciding what to fund. This program was really focused on mature software, not like early stage prototypes, but really think about the core software libraries that are used by virtually anyone in a given field of the life sciences. And so we assessed it across these 5 criteria: existing impact and adoption in the respective community, the quality of the project from an open source perspective, how compliant it is with best practices in open source maintenance and development, the feasibility of the plan of work, of course, diversity, so steps taken to ensure diversity inclusion among contributors of the project, and finally, the overall value of the proposed work to biomedical users as a key audience that we're trying to serve through this program. And one of the great things about doing this is that as a side effect of running the program, we collected a lot of data about the larger open source ecosystem. And so while of course it's not perfect data, it's data from projects that responded to an application, so it's biased in many ways, but it's a really interesting data source to understand, for example, the distribution of mature software development practices in the community. So for example, this gives you a quick summary of the adoption of specific open source development practices, for example, the availability of code of conduct or continuous integration or end user documentation among funded projects and among the larger set of applications that we received. And so you'll see, unsurprisingly, that was like one of the intended goals of the program, that the adoption of these practices is like a consistently higher among the funded projects, and that it's like those represents like a benchmarks that projects aspire to become mature and serve an entire community should probably aspire to adopt. We also, as part of the selection process, so there's like a traditional selection process that involves like experts for each application. We identified both domain experts as well as open source practitioners to have at least 3 to 5 data points from experts can really like judge and evaluate the application against those 5 criteria that I mentioned. But also as a supporting tool, we provided some descriptive statistics pulled from the code repository. These are not, I'm talking here to the CHAOSS community. These are not by all means like a really sophisticated metrics. They're really descriptive metrics that help support the decision-making process. So we ask our reviewers not to make decisions based on these metrics alone, but it basically helps situate a project in the context of the entire pool of application received. So for example, you can see here, this figure in gray that we computed gives you the percentile for that specific metric with respect of the pool of application we received. So Galaxy, unsurprisingly, is a very popular project. It's in the 88th percentile of stars or 95th percentile of forks with respect to the pool of application received in that cycle, right? And we also generated some plots just to give reviewers a sense of the level of activity in the most recent years for the project. Another key data point that we collected that was really critical is qualitative data solicited from the applicants about the landscape. The landscape for these tools can be very different. We can have like a proprietary or open source tools that compete with this software. And we thought it's really important to hear from the words of the maintainers how the project is being used and how it compares to other tools that are used in the field. For example, is there a different feature set that the software offers? Is it replacing proprietary software in some fields? And I can't emphasize enough how this section provides like a immensely useful qualitative data to help position software within its niche and within the context of other tools that are being used in the field. I'm not going to go through all the other details of the evaluation, but like I said, it's based on these 5 criteria, and there's more detail about the specific questions we ask the reviewers on the public presentation of the program. But I want to share more about data we collected after the fact to assess the impact of funded projects, both individually and as a whole, for this program. And so we embarked in a project to try and answer like a comprehensive set of questions about the needs in the open source community in science. We support the types of activities that the funds were mostly used for and most useful for. And the immediate impact of the short-term impact, I should say, of the funded project, the program, both on the project themselves, on the open source ecosystem at large, on diverse participation in general, and specifically in biomedical research as one of the goals for this program. We use a variety of sources. I can share more about the data sources we used if it's useful. Maybe we can keep that for the Q&A. But I'm gonna start with some of the qualitative data we collected. So we ran a survey among the funded projects to try and understand beyond the specific gaps for which they requested funding, what are gaps that they have that could receive support? Again, keep in mind that this is not just scientific open source projects in general. It's a selected number of projects that have been assessed by experts as a critical or essential open source tools using the respective communities, right? So it's like an interesting curated sample of projects that fall under that definition. And you see, for example, here that unsurprisingly, sustainability planning is one of the most urgent needs identified in this community. And there's a variety of other needs in technical capacity among these groups have been identified as in high demand. Looked also at gaps in documentation capacity and what these projects would need support with. Some of these are like less urgently felt as the technical needs or the sustainability needs, but nonetheless quite important. And finally, an area that really emerges having a tremendous need of support, unsurprisingly, given what we know about how open source communities work, is really gaps in community-related capacity. So we saw a variety of activities for which many of these projects, despite being tremendously successful in terms of like a global adoption and global support, many areas where they would benefit from additional support. And all these areas of activity should look familiar if you're active in open source communities. We also looked at the type of outputs reported by grantees, and so it was interesting to see that the variety and the breadth of outputs that the funding produced. And so there's like more granular data in a report that we published about the specific types of outputs that these fundings produced. It's interesting that includes a variety of traditional outputs for open source communities, as well as outputs really more focused on research-related activities, such as data or manuscripts or presentations. And this gives you like a little bit of background of how these were distributed across the funded activities. And given the stated purpose of the program, the community and open source focused ones still represent the vast majority of funded activities that resulted from this initiative. I'll just pass briefly on this, but we also looked at like the type of support, where the funding went in terms of like what type of aspects of a project the funding supported. And it's very interesting to see, for example, that 85% of the respondents among funded projects reported that the funding was critical to support the primary maintainers, among other things, like surfacing how even supporting people and their time and buying their time, especially if they're academics and their primary job is not to produce software, is really one of the key areas where we can allocate funding. And we were very pleased to see that over half of the projects were able to use the funding to support directly activities to enhance diversity and inclusion in their respective communities. And This type of activities specifically cover a broad range of interventions and also different dimensions of diversity and inclusion. And so this just to give you a quick breakdown of the type of work that we're able to support um, through this program in the area of DI specifically. And finally, really none of this would matter if, given that we work for a science funder, and ultimately, like the primary thing that our decision makers care about is really like the impact that all of this is having on science and scientific communities. We looked at the type of impact that the short-term impact that the funded projects had on science and on their downstream users. And we had a blend of quantitative and qualitative data that really helps them characterize the type of impact that we're having on scientific communities. And this is just like a high-level set of examples, like really small qualitative vignettes about the type of work that this program supported that directly introduces features or technical capabilities that are meant to support an audience of biomedical researchers. And these are just high-level, like cherry-picked highlights. But if you want to have the entire story and both the full quantitative and qualitative data, we published this monster report just a couple of months ago. It's available on Zenodo. It's 80 pages full of all the data that we use and we collect, again, qualitative and quantitative data. That hopefully can give you a sense of like what we're able to learn about the funded projects. And I want to close with a note about some data that I wish we had, and that in fact is still like sorely missing from this ecosystem, that I think funders, institutions, and the maintainers themselves would find tremendously useful. And I want to start with like some questions that right now are really, really, really hard to answer, given the lack of data to support them. What software tools are most frequently used by scientists in any given field? What is the adoption of open source compared to proprietary software in any given field of science? What new tools are replacing legacy ones, again, on a field-by-field basis? Are specific fields transitioning from one programming language to another programming language? What type of software should be part of a computational curriculum of an undergraduate student wanted to build a career in any given field of science? And what tools are used in some of the breakthrough papers in any given field to support those research questions? So some of these are like really high-level questions, but for which there isn't any comprehensive large-scale data source. We can do this on a case-by-case maybe basis, but there really isn't a universal comprehensive data source that we can use to try and answer these fundamental questions that ultimately, as funders, we care a lot about if we're trying to make the case that software needs to be supported as a service to science. And the way that I like to characterize this is that over the course of decades, really since the half of the last century, we've developed like a really comprehensive set of reference data sets and tools and services around papers and their dependencies. So we now have a comprehensive citation databases and citation graphs that really help us understand the influence of papers on papers, if you wish. So we can construct all kinds of metrics and blend them with qualitative data about the impact of science on science. And at the same time, thanks to, among other things, the work of groups like CHAOSS, we have a variety of tools that help us understand the impact of software on software. So through dependency analysis, by looking at code contribution histories, we have a fairly articulated way of characterizing the health and growth and mutual dependencies of software projects when it comes to software influencing software. What we don't have, or at least we don't have at scale yet, is quantitative data that helps connect scholarship, so the the narrative version of science that we distribute and share in the scientific community, and its computational underpinnings. And I think trying to figure out like what data sources we have that connect these two words is going to be a critical contribution that we can make to supporting scientific open source going forward. The reason, I'm not going to spend too much time on this, but as we all know, like software citations are not prevalent in science, despite the fact there are formal proposals on how to do this. The vast majority of scientific papers do not formally cite software, and when software is referenced, it's typically just mentioned informally in the methods section of a paper, if it's mentioned at all, but typically not in a way that is machine readable or easily extractable from a paper. And there's been a growing number of efforts, primarily academic efforts and research efforts, at characterizing the links between software and the literature. Many of these have produced really impactful data sets, but they tend to be primarily studied data sets or research paper, as opposed to data services comparable to a citation database that we may use, for example, in bibliographic analysis, bibliometric analysis. And one of these projects that we contribute to ourselves is the CZ software mention dataset. So this dataset, to our knowledge, represents the largest open dataset of software mentions mined from the biomedical literature and mapped to code repositories and unique identifiers for software. So we were able to extract through a process that I'm not going to go over, but you can find all the methodology in the preprint, up to 7 million individual mentions from a corpus of 20 million papers. That basically allows you to say, okay, there's a reference to image, an informal reference of image A in the paper. How can we normalize it and map it to a canonical identifier of that software? And what's really cool about this is that once you start having that data, you start applying it, you can start conducting some analysis. For example, this one, which again, as I mentioned to Claire in a previous conversation, this was not used as part of the assessment of what projects to fund, but it gives you basically an understanding of, through the lens of mentions of software in literature, of how fast specific tools are growing over years, and help you give a proxy of their popularity, of the speed of their growth. If as a funder, you're interested in knowing if a project is growing like much faster than it was, or maybe slowing down, or maybe it's becoming like a disproportionately popular in the field, this data can be really handy. And it helps you, among other things, show, like, this is a log scale so it shows really some of these projects, just in terms of how they're mentioned in the literature, they've grown by orders of magnitude over just a handful of years. And this is like a data point that we're using as a way of like surfacing the urgency of supporting scientific open source. Funding for scientific open source is not tracking with its usage by the community, and that's a fundamental problem that, as a funder community, we need to address. I will mention, this might be particularly interesting for this community, that this type of data can also be used for answering some other questions. For example, questions that relate to software as it's built and maintained within the context of institutions. We know it's pretty hard to be able to say, my university produces and maintains all these software products. Even like keeping an inventory and a registry of this project is kind of challenging. And so some of the projects that we supported through a hackathon that we hosted 2 years ago are trying to look, for example, at ways of linking software to the research organizations that they're affiliated with through ROR-IDs. There's one project that was born out of this hackathon that's trying to look at this connection specifically. And then we had other projects, such as like identifying links between papers and code repositories, combining software mentions with dependency graph to try and understand what are the most critical dependencies of software that gets mentioned very often in the literature. And then also analyzing reasons why people are mentioning software in the first place in paper. So as you can imagine, there's an entire research program and a potential set of like data services that we don't have yet at scale that could be produced if this data existed at scale. So the message is that we need much better data infrastructure to support the scientific open source ecosystem that goes beyond dependency analysis or analysis of code repositories. And these are just examples of things that we need as a funder community, as an institutional community, to be able to support these projects. And I want to just finish with one very concrete example of why such a thing is so urgent and it's ridiculous that we don't have it. Tom Caswell is one of our grantees. He's one of the maintainers of Matplotlib, who I'm sure, as you know, is one of the most widely used Python library for data visualization. And in the process of running, like submitting an application to a call from NASA, was asking on LinkedIn, please send references to papers, projects that fall under any of the NASA missions and use Matplotlib. So the very idea that somebody should resort to crowdsource requests for information to answer something that when it comes to citations, we can readily answer by looking up a number on a database is something that today, given the centrality of software in science, should not be an issue, right? And so just to conclude, some takeaways, we're fortunate that open source is data rich. And so we have a vast amount of quantitative and qualitative data to help inform these efforts. And yet we have enormous gaps in producing what I call these comprehensive data to map the reuse of software and open source specifically in science. And can I emphasize how metrics are insufficient and qualitative data is absolutely critical, especially for decision makers to build a case in support of these tools. So we don't only need to rely on quantitative data. It's absolutely critical for us to be able to obtain compelling narratives to sustain these projects. And yes, metrics suck, and everybody hates metrics, but we need them. And I think our goal, and again, preaching to the choir here, is to develop like metrics can be responsibly used by funders, and that reflect the needs of the communities that we're aiming to support. And finally, metrics are products, so we need to move beyond the stage of research projects or one-off data sets to try and quantify again the impact of software in the literature. We need to get to a point where like looking up the impact of software tools should be as easy as looking up citation of a paper, and we're not there yet. So I think that closes my presentation. And sorry, it took a bit longer than I was expecting, but looking forward to any questions you may have.
Awesome. Thank you, Dario. I'm guessing there are a number of questions. I do want to point out to you, Dario, that there's a comment from Lorena in there with respect to some work that she was part of before.
Yep.
So just so you don't lose that.
Yep. Thank you. Yeah, I'm seeing now all the questions in the sidebar. Yep.
Okay. Jonathan, I think you were first.
Yeah, thank you for that. That was fantastic. And of course, I have to thank you for EOSS anyway. Many of our projects in Focus are beneficiaries of it, and we see the anecdotal impact of it every day. It does a lot of good. Okay, so you mentioned a lot of different things that need to get done. I agree with all of them. I'm personally trying to tackle several of them from an entrepreneurial perspective to get to the state that you're trying to get it to. But I'm really curious of the list that you gave, and there were probably like 20, and then there were a couple you just glanced over, like software projects don't track their funding data, which is a problem in itself. What are the highest three that you would find useful from the funder's perspective?
Yep. Yeah, that's a good question. So I would say, and again, that was like the main message of the second part of my talk, that data that allows you to connect a software product to paper as an output is really critical, because you can imagine in aggregate, if I want to know, let's assume for a second that I only fund projects that are using, I don't know, structural biology or the earth sciences, right? Not having that data that tells me what my communities are relying upon in terms of like software is really a critical gap. And the one thing we've heard from all the funders we work with is that having that data that can help understand the adoption of software within the specific communities they're funding is the number one gap. And so I would say that's definitely one of the top priorities. I would say the other one, maybe the runner-up, is this funding history. It's given that software, unlike papers, well, it's not entirely true, but like software, especially like software that is like so like global in nature, that has like multiple groups contributing and can receive funding from multiple sources. It's really, really hard to have a comprehensive view of who funded what and who funded what part of a project. And so coming up even with a better way of representing um, the funding history over years of a project as a whole is something that would be tremendously useful for funders. I will mention that we did collect a self-reported funding history, which again is biased. It's limited to whatever the PI is aware of. But even studying those like mini funding histories is tremendously, I mean, that in itself could be a PhD thesis, like looking at software maybe funded for years at a multi-million level by a government agency, becomes critical in the field and then stops having funding, right? That's one example. Or then you have like software that's never received funding, but it suddenly becomes like a universally used in the field for which our grants were the first ones that they ever received. So the natural history of funding is another area that's like tremendous gaps in data. And for funders, being able to understand like the history of this funding is something that would be like really, really useful for decision making. So I would say these are the two. I mean, there are so many gaps here, but these are the two like data gaps that I think are particularly acute for funders, if that makes sense, Jonathan.
Yeah, absolutely. I just had some great conversations at FOSDEM with the ecosystems folks exactly about these two. So hopefully there's some solutions coming.
Yeah.
Thank you.
Yeah, Maria.
Hi, Dario. I'm community manager of Bioconductor project, so also thanks for funding us in a few EOS grants. I really actually first I've actually got two questions, two quickish ones. One is related to the last question or what you were talking about in terms of grants. When you were looking at the software mentioned, did you look at any of the funded grant proposals, like the NIH Reporter grants that are publicly available, to see what software was used in those? Or was it was research papers, was it?
Yeah, it's purely, that's a great suggestion. So we only looked at the literature and preprints. So, and it was a corpus. What I didn't mention is that, of course, even obtaining a comprehensive full text corpus of literature is a challenge because of the fact that a large fraction of that literature is not openly available or openly mineable. But that 20 million paper corpus was exclusively scientific papers and preprints. So we did not look at, for example, federal grants, which I agree with you, represents another tremendous source. So governmental grants and their mentions of software and maybe any public reports associated with these grants could be another tremendous source of data to answer that question.
Okay, great, thanks. And my second one actually follows on from that. Like that was a great data set that your group made, the CZ mentions, and I appreciate it was a massive amount of data and probably a massive amount of work. Is there plans to continue on or do anything more with that project?
Yeah, so that's a question we've been receiving a few times. We released a couple of snapshots of this data set, but also we don't really have it's the organizational capacity or mission to maintain that or grow it into an actual data service. So I was actually very excited to see that there are many initiatives underway, which I learned about at the International Research Software Funder Forum in Sweden in September. Just to mention a few, OpenAir, DataSeer, and EuroPMC, they're all building pipelines that are trying to answer that question using like building data services, not just doing like one-off data set generation. And so, and some of them are reusing some of the seminal work that James Hausen team did with SoftSci. So they're like very similar approaches to the CZI data set. And what I like about them is that they're really trying to scale these efforts and turn them from like a static data set or a research paper to an actual service. So I think the answer is that while we're not directly maintaining or productizing that data set, we made all the code available and all the snapshot available to the community, including the algorithms. We're optimistic there will be efforts that can pick up these initiatives and try and build them to something more reliable.
Thank you.
Yep, Jonathan.
Just very quick to Maria, there's a group that we're putting together that's a hackathon that includes the folks that did that original data set, some additional folks, and a lot of the people that Dario just mentioned to move this forward really quickly. If I can put some information in the chat if anyone's interested in helping extend that data source and that pipeline.
That'll be brilliant. Thanks a lot.
Absolutely.
Yeah, and I see some comments and questions from folks on the call. Yeah, a reference from Lorena about the NSF survey. Thanks. I think I remembered that data source, so I'll definitely check it out. And then
Richard may have a comment or question on the
Richard.
link
I have
put
an
in there.
exceedingly dumb question, which I may have missed it, and I was just curious. You've tracked 20 million papers. You've looked at a crap ton of software packages. That's great. Those are two things. We also have university mapping, and we also have the idea of just mapping people directly and just ignoring software and ignoring papers, but just make a giant database of who's actually doing the work for this sort of stuff. And I just wonder, have you tried building either of those two databases and then cross-referencing everything? And again, I may have missed this, but I'm just wondering, like, what would it cost to just fund all the people doing the work?
Yep. Yeah, that's a good question. And I will share the link here. Give me 1 second. So the short answer is that that is not data that we produce, but there were groups at the hackathon that we hosted in 2023 on the heels of this data that we released. They were looking specifically at connecting ORCIDs and software contributions. And so that's a partial answer to of that suggestion. And I don't know who's doing that work, but it's definitely like a few folks in the community that are looking at that specific problem.
Cool. Okay.
Mhm.
Thanks.
Yep. Edit. Hello.
You're muted at the time, Aiden.
Might have poor sound. She's on a
Got it.
train. We were talking. Oh, they got it.
Sorry, I'm still traveling, so I apologize
You're good.
for being off camera and everything like that. Again, thank you, CZI, for funding our work. It's absolutely invaluable to us and funding we wouldn't get from any place else. So really appreciate it. Dario, just thinking about one of the issues that we've been discussing within kind of bioconductor community, which is publication of workflows. And by workflows, we're meaning kind of like tutorials. We're bringing in lots of different software packages and showing people how we can connect different software together within an ecosystem to perform an analysis. previously, Mike Love and a couple of others had done a really nice job of publishing code, actionable code, and getting those published. And that was within F1000 or whatever. But although it's something that's mentioned tons of times within, I don't know how many journals have said it, it's still difficult to publish code with publications. And if that was done, it would be really easy to see exactly who's using what and where and how. And even where people are using supplemental, like, oh, go to this GitHub, half the times the links don't work. And then if people publish something as a supplement, it hasn't a DOI. And you may or may not find it. Supplemental material in website, oftentimes they're not right. And like one of the things we wanted to be able to do was also be able to version it. So, that workflow was 6 months old. Now we're recommending this modified version, or somebody updated one package within that computational pipeline, and now it's no longer like a valid, it doesn't work anymore. So replace this in with it, or having kind of live, citable, publishable software that's beyond just like kind of workflow, but actually does that tutorial thing. There isn't any journal that wants that.
Yeah, fully agree. There's like another dimension of the problem. We know that, I mean, it's really like it's the impact of the paper-centric culture of science, right? Where like if you think about the metadata to describe software-related contributions, the um, uh, everything you find that is not indexed, that is not as an identifier, that's like attached to a paper with like data or other resources that is not visible, or is not easily referenceable. Like all of these like really like a result of the culture of scholarship that we've been building over the course of decades. And when it comes to papers themselves, I mean, the closest that comes to mind is JAWS. So as a journal that's trying to address those needs. But again, it's a niche example.
Yeah,
And
yeah, and we've looked at JOS, but they tend to be very short papers and not
right.
necessarily describing kind of like, these are why these tools work together
Yeah.
or whatever. And then it's not, it's having the code that's actual that somebody can try it out. I don't know. It seems like theoretically it's a simple solution, but actually in practice it's really difficult. And we talk about kind of, people will cite the method that's in the software, but not the software, because the method is citable, because that, when it was published, was new science that was benchmarked.
Right.
But the software, then, if there's you don't get rewards in science for making good software. You get it for doing an innovative method. And equally, you don't really get points for making data sets and resources available.
Yeah. I completely agree. Like I would say like um, of course there's a significant developments underway to make sure that data in itself is a citable, can accrue credits and citations. When it comes to methods, we've been working in the past with this project called protocols.io, which some of you may be familiar with, which is really like a repository. Like the goal is precisely to make sure that methods become standalone citable objects that can be referenced, version controlled. And at some point, while that project is primarily focused on wet lab methods, there's actually a growing set of computational methods that they also cover. And so that could be an interesting venue to explore, because it can also represent like a step-by-step. Again, it's really primarily designed for wet lab protocols, but it does include like the ability of representing computational workflows and computational protocols. And it comes with some of the GitHub-like community features, like submitting comments and pull requests and version control that you'd expect from a code repository you cannot find in a journal. So that might be another interesting venue to consider.
Cool.
So, Jonathan, do you have a last comment? Because we're right at the end of our time here.
Yes. Is there a way to reach out to you? I have something I want to show you that I work with a project that may productionalize what you're asking for, and I just want to see if it is. And the question for Dario, so this question about citing methodology and being able to mint 10,000 PIDs for any single piece of software, I think it's speaking to deep tech, deep infrastructure that is underpinning kind of the entire software development process, the data storage process. Is that something that you slash CZI are looking at as a potential focus area in that solving some of those deep issues might solve some of the upstream issues?
Yeah, I would say that's something that not just CZI is looking at, but the funder community is probably looking into. So we are part of a growing community of funders that has a specific focus on open source software and research software. And so I would say that within that community, there's a strong set of shared needs that are really not just for a single funder. Like what you're describing should really be a service to funders and institutions as a whole. And so short answer is yes, I think it will be interest not just by CZI, but within the community as well.
Great,
All
thank you.
right. Well, we are at the end of time. I suspect this could go on for a while, Dario, but I think you're kind of busy this week. So maybe you can get back to some other things. Let's all thank Dario for coming. This was really awesome. We all learned a lot. Dario, thanks for taking some time to join us today.
Having me. It was super
Appreciate it.
fun. Yep. Glad to see you all.
All right, everybody. Thanks for coming and take care.
Here.
Thank you. Bye.
Bye.
I don't want it to stop.
It's over. You got to go. See you later.